Okay, everybody, how are you doing? Hope you're fine. Today, going to do a very short video about an idea in econometrics called conditional mean independence. And it's a short, brief idea, and let's get right to it. Conditional mean independence. So, um, normally, we'd have a regression if we had a two variable regression. We'd have a regression like this, where the outcome y is a function of beta 0 plus beta 1 times x1 plus beta 2 times x2 plus some error term that takes into account measurement error and all other factors. Um, and normally we make the assumption that the expected value of this error term, conditional on the x1 and the x2, that is conditional on the x1 and x2, is that it's equal to 0. So that's our normal assumption that the other factors and the measurement error, conditional on the included variables, the x1 and x2, on average are equal to 0. That's sometimes a strong assumption. So what we'd like to know is there a somewhat weaker assumption that we could use that would still give us an estimate, an unbiased estimate of the coefficient that we have that's of interest. And the assumption of conditional mean independence is that, yes, we can do that if we're only interested in the coefficient on one of the variables. So say we're only interested really in beta 1. That's the coefficient that we're interested in. And we're not really interested in beta 2. We just have the x2 here as a control variable. So we know that sort of parental education affects child education. We know that parental income affects child education, but we're not really interested in the relationship between income and education. Instead, we're really focused on the relationship between parental education and child education attainment, right? So we might be particularly interested in that relationship, and the other relationship between income and education is really not our concern. Um, so, and that's true in many cases, right? We have a particular relationship that we have in mind, and all the other included variables are, we call them simply or merely control variables. We're not interested in their coefficients per se. We're not interpreting their coefficients as causal coefficients. They're not relevant for policy. So conditional mean independence says if it is the case that we're only interested in one of the coefficients in the multiple variable regression that we're estimating, then we can have a weaker assumption. And here's what the weaker assumption looks like. So the weaker assumption is that, let me just get the weaker assumption is this: the expected value of the error term conditional on x1 and x2 doesn't have to be equal to 0. It has to be equal to the expected value of the error term conditional on x2. That is, once we control for x2, x1 doesn't have any additional correlation with the error term. So once we control for x2, the remaining error that's in there, the other factors, are not correlated with the x1. So that'll be the assumption that we need. It's a weaker assumption that the other factors are not correlated with x1 or x2 or complicated relationships between x1 and x2. This is a weaker assumption. Once we control for x2, the error is not correlated with x1. Is a simple version of the way we might say this. If that's the case, then beta 1 hat is an unbiased estimate of beta 1. And let's go straight to the proof and show that. So first, let me clear this, and let's go ahead and show this proof. It's fairly straightforward, and we're going to do a simple proof. To do the simple proof, we'll make a simple assumption. We'll assume that the expected value of the error term conditional on x2 is linear in x2. So the error will look like this. The expected error conditional on x2 is just gamma 0 plus gamma 1 times x2. So the higher is x2, the bigger is the error. That's all our assumption that we're making. The higher is x2, the bigger, more, if gamma 1 is positive, then the error is more likely to be positive. If gamma 1 is negative, the error will be more likely to be negative error. So that's our simple linear relationship that there's some pattern, because remember, the expected value of the error conditional on x2, we're not assuming is necessarily equal to zero. So we just adopt some simple pattern in order to show this proof. And the proof can generalize. We'll just do it for this simple pattern. So gamma 0 and gamma 1 are constants. They're just numbers. They're parameters in our underlying population relationship. And we don't need to, there's some conditions under which this will be true. We don't need to worry about them now. We'll just make this assumption. So we're assuming that there's this linear relationship. All right, let's go on to step 2 of our proof. So here we go, slightly longer page, but this is all we need for the proof. So we assume that the expected value there is conditional on x2 is linear in x2. So we assume this. Now what we're going to do is define something called v1 to be this term. It's going to be epsilon 1 minus the expected value of epsilon 1, which is our original error, conditional on x1 and x2. And remember, this term here is not equal to zero. That's by assumption, it's not equal to zero, right? We normally make that assumption that it's equal to zero, but in this case, we're not making that assumption. We have this weaker assumption that we made. Go back in the video and see what the weaker assumption is. So this is not equal to zero. So there's no reason why epsilon I minus this is equal to zero. So VI is something that we define. Now, while epsilon I minus the expected value here is not necessarily equal to zero, we can show that the expected value of VI conditional on xi, x1i, x2i is equal to zero. And the reason for that is we'll just write it out here, the expected value of this. We'll use our definition of VI and we'll just plug it into here. So that's what VI is. Notice what we have here then is an expectation term and another expectation term. And if you remember from your earlier statistics class, we need to apply the law of iterated expectations. The law of iterated expectations, the expectation of an expectation. If you apply that law, what you get is that these two terms, the expected value of this term, conditional on x1 and y2, minus the expected value of epsilon I conditional on x1, x2, conditional on x1, x2. It's just the same thing. It's the expected value of epsilon I conditional on x1 and x2. So these two are the same thing. So that's equal to zero. So the expected value of VI conditional on x1 and x2 is equal to zero. So we established another preliminary result. And now we can move on to our full proof. So clear this out and jump down to the next page. There we go. And you want to go back and look at the algebra here and observe this very slowly until you're pretty clear in understanding the proof. Here's our original equation. So this error term is the problem. So we're going to substitute for the error term, we're going to substitute this. Notice by our definition of VI, which is epsilon I minus the expected value of epsilon I conditional on x1, x2, that these two are equivalent, that epsilon I alone is the same thing as the expected value of epsilon x1 conditional on x1, x2 plus VI. They're the same thing by definition. Now, our conditional mean independence assumption was that these two things are the same thing. The expected value of epsilon I conditional on x1, x2 is the same thing as the expected value of epsilon I just conditional on x2, right? So that's the difference here. We substitute this in here. Let me change color here so we can go on. Now, we made an assumption, just for simplicity, that the expected value of epsilon I conditional on x2 was just a linear function of x2. So we plug that in here. Well, now we have a common factor, x2 here and x2 here, and we can associate this gamma 0 with this beta 0. These are just parameters. So we have beta 0 plus gamma 0, and here we have beta 0 plus gamma 1 times x2, right? Common factor here, x2 and x2. So now we have, we'll just call this delta 0. So these two terms added up, we'll just call it delta 0, and these terms added up, we'll call it delta 1. Now we have an equation that looks just like our classical regression equation. And remember, we just showed that the expected value of V1 is equal to 0. Go back again into the video and see. So this equation solves our normal ordinary least squares assumptions. So beta 1 will, if we estimate this with a sample of data, our estimated beta 1 hat will be an unbiased estimate of beta 1 because this satisfies the ordinary least squares assumptions. But notice that our estimate of the coefficient on x2 will not be beta 2. Our coefficient will be beta 2 plus gamma 1, but we don't know what gamma 1 is, so we have no way of recovering what beta 2 is. So, but that's okay, because remember at the front, we're not interested in beta 2. So we have an unbiased estimate of beta 1 and with a weaker assumption about the distribution of the errors. So that's the idea of conditional mean independence. Encourage you to watch this video not once, not twice, not 3 times, but 4 times. 4 times until you feel more comfortable understanding what we're doing here. Go back and look at our ordinary least squares proof that if the expected value of the error term conditional on the included variables is equal to 0, for the single variable regression we did the proof, then the estimated coefficient is unbiased.